Far out in the dark sits a region so empty that 2,000 galaxies should be there, and barely 60 are. Yet scientists keep catching signals from places like this. A dead star that blinks every 6 hours and refuses to go quiet. A ring of galaxies so wide, it bends the rules of the whole universe. We are heading somewhere our own science says should be silent. If this kind of mystery keeps you up at night, like and subscribe and come along. Take a breath. We begin. Look up on a clear night and the stars seem scattered at random. Zoom out far enough, past our galaxy, past 1,000 more, and a hidden order appears. The universe looks like a giant spider web made of light. Galaxies almost never float alone. They string together into glowing threads called filaments. Some of these threads stretch for hundreds of millions of light years, far longer than anything your mind is built to picture. Where the threads cross, they pile up into bright knots packed with thousands of galaxies. Astronomers call those knots clusters. So far, this sounds full, crowded, busy with light. The strange part is what sits between the threads. Picture the foam on top of a soda. The matter of the universe clings to the thin walls of the bubbles. The inside of each bubble is mostly nothing. Those dark gaps have a name. Scientists call them voids, and voids take up most of the room in the cosmos. Around 8 out of every 10 parts of space is this quiet, empty, dark. Here is a number to sit with. Inside one of these voids, you could fly in a straight line at the speed of light for 100 million years and pass almost nothing at all. No stars, no planets, no glow, just black space rolling on and on. This web is real. It has been mapped by surveys that pin down the spots of millions of galaxies, one by one, building a three-dimensional model of the sky. The threads are confirmed. The clusters are confirmed. The huge dark bubbles between them are confirmed. For a long time, those bubbles were treated as background, boring, the empty parts you skip past on the way to the bright stuff. Then telescopes grew sharper, and people started looking closely at the dark. What they found broke the calm. One of these holes turned out to be so wide and so empty that the first astronomers to map it thought their machine had failed. They checked the equipment. They checked the math. The machine was fine. The math was fine. The hole was simply there, a piece of the sky with almost nothing inside, sitting in plain view above our heads, and it was waiting to be named. In the year 1981, a team of astronomers was doing slow, patient work. They were measuring the distance to galaxies, one after another, trying to draw the first real map of how the universe is laid out. Their leader was a researcher named Robert Kirshner. The work was simple to describe and brutal to do. Point the telescope. Catch the light of a far galaxy. Measure how stretched that light is, which tells you how far away the galaxy sits. Write it down. Move to the next one. Repeat for years. As the dots filled in, a pattern grew. Galaxies clumped where the team expected. Then they reached a stretch of sky near a constellation called Boötes, the herdsman, and the dots stopped, not for a small gap. The blank kept going. They aimed deeper, expecting galaxies to appear. The sky stayed dark. They aimed wider, still dark. A vast round region of space sat in front of them with almost nothing inside it. The team had found a hole in the universe. It became known as the Boötes Void, and people soon gave it a blunter name: the Great Nothing. The size is hard to hold in your head. This empty bubble stretches around 330 million light-years across. Our entire Milky Way galaxy, with its hundreds of billions of stars, could fit inside that gap billions of times over and still leave room to spare. Think of the largest empty desert on Earth. Now shrink that desert until it is a single grain of sand. The Great Nothing is the desert. Everything we usually call space is the grain. The center of this void floats about 700 million light-years from us. That means the light showing us its emptiness left on its journey before the first dinosaurs walked the planet. We are staring at an ancient hole. When the discovery went public, the reaction split. Some scientists were thrilled, others were uneasy. A gap this large was hard to square with how matter was supposed to spread out after the birth of the universe. The team was sure of one thing: the void was real. It was confirmed by the data, checked and rechecked. The unsettling part was the meaning. Why was it there? How did a piece of the cosmos end up scrubbed so clean? And there was a sharper question hiding underneath, one that turned the emptiness from strange into almost frightening. The math said this region should hold a crowd. It held a ghost town. The difference between those two numbers was about to get personal. When astronomers add up how matter should spread across the sky, they can predict how many galaxies belong in any chunk of space. It works like counting people. Give me the size of a city, and I can guess the size of the crowd. So they ran the numbers on the great nothing. For a region that wide, the rules of the universe called for around 2,000 galaxies, 2,000 glowing cities of stars, scattered through the dark. Then they counted what was really there: 60. Sit with that gap. 2,000 expected, 60 found. Imagine walking into a stadium built for a sold-out concert, a place meant to roar with the noise of a packed crowd, and finding 60 people rattling around inside. The silence would feel wrong. It would feel like something had happened. That is the great nothing, a space carved out for a multitude, holding a handful. For years after the void was named, the count kept teasing scientists. They would aim a sharper telescope into the dark, hoping the emptiness was a trick of weak eyesight, hoping the galaxies were hiding just out of reach. A few more would turn up, one here, a faint smudge there. Slowly the tally climbed towards 60 over more than a decade of searching. It never climbed close to 2,000. The hole stayed mostly empty, no matter how hard anyone looked. This is where the void stops being a fun fact and starts poking at something deep. The early universe was almost perfectly smooth, like a still pond. Tiny ripples in that smoothness grew over billions of years, pulled together by gravity, until they became galaxies and clusters and threads. The smooth pond turned into the foam. A void this clean means the ripple here was unusually faint. Matter drained out toward the edges and never came back. The few galaxies still trapped inside drift far apart, each one alone in the dark, with no neighbors close enough to share a night sky. And that raises a haunting picture. What would it feel like to live in there? Picture a planet circling one of those 60 lonely galaxies, somewhere near the heart of the void. Picture intelligent life on that planet, looking up, building telescopes, asking the same questions we ask. They would aim those telescopes outward, searching for other islands of stars. And in almost every direction, for an unthinkable distance, they would see nothing looking back. Their sky would be a wall of black. One scientist put this idea into words so chilling that it has followed the Boertes void ever since. It is a single sentence about loneliness on a scale no human has ever felt. And it changes how you think about your own place in the dark. The astronomer who first said it was named Greg Oldering. He was trying to explain, in plain language, just how empty the great nothing really is. The line he landed on goes something like this: if the Milky Way had been sitting at the center of the Boertes void, we would not have known other galaxies existed until the 1960s. Let that picture form. In our real history, humans figured out that other galaxies exist back in the 1920s, when a scientist named Edwin Hubble proved that faint smudges in the sky were whole separate cities of stars far beyond our own. Now move us into the void. Same telescopes, same curious minds, same drive to look up and wonder. But the nearest galaxies are now so far away and so dim that our instruments simply cannot catch them. For decade after decade, we would have stared into the black and concluded that the Milky Way was the entire universe, that we were the only thing there was. Oldering was not giving an exact date. He was painting a feeling. He was telling us how far you would have to look from the center of that void before anything at all turned up. As a way to feel the emptiness, it lands like a punch, and it carries a lesson that reaches far past one empty bubble of space. Where you stand changes what you can know. A civilization born in a crowded part of the universe, near bright neighbors, would grow up certain that the cosmos is full of company. A civilization born in the deep of a void would grow up certain that it is alone. Same universe, same physics. Two completely different beliefs about reality, decided by nothing more than a cosmic address. Here is the unsettling turn. We have always assumed our own view of the universe is honest, trustworthy, a fair sample of how things really are everywhere. What if it is not? What if our address is also strange in ways we have not noticed? What if the part of space we can see is quietly lying to us about the whole? This idea is hard to test, and scientists treat it with care. It sits closer to a deep question than a settled answer. But the question refuses to go away because of something astronomers found much closer to home. It turns out we may not be living in a crowded, ordinary neighborhood after all. The Great Nothing is the most famous hole in the sky. It is far from the only one, and the next void on our list is the one that should worry us most because of where it sits, right on top of us. For a long time, we pictured our galaxy as floating in a normal, average patch of the universe. Nothing special about the address, a regular street in a regular town. Then astronomers started counting the galaxies around us, out to great distances in every direction. They were checking a simple thing. Is our corner of space as crowded as the cosmic average? It is not as crowded. It is emptier, noticeably emptier. The numbers point to our Milky Way sitting inside a large, underdense region, a void of our own. Scientists have given it a name, the local hole, and some studies stretch it out to a staggering size, perhaps 2 billion light-years across. If those measurements hold, it would be one of the biggest known underdense regions ever mapped, and we are parked near the middle of it. To be honest about the science, the exact size and depth of this hole are still argued over. Some teams measure a deep, wide void. Others read the same sky and see something milder. This one lives in the space between confirmed and unknown, and good scientists are still fighting about it. That fight matters, and here is why. If we really do live inside a giant emptier bubble, it would mess with one of the most important measurements in all of science, the expansion of the universe. Picture a crowd in a stadium standing up to leave. If you are stuck in a half-empty section, the people near you spread apart faster than the packed sections far away, just because there is more room. Sitting inside a void does something similar to the galaxies around us. They appear to rush away a little faster than the deep, crowded universe beyond. That false speed could be fooling our instruments. For years, scientists have been wrestling with a stubborn problem. They measure how fast the universe is expanding using two different methods, and the two numbers refuse to agree. The disagreement has a name, the Hubble tension, and it has become one of the loudest puzzles in modern science. Some researchers think our local hole might be part of the answer. We could be reading the universe wrong because we are sitting in an unusual spot, watching nearby galaxies flee a little too fast, and mistaking that for the behavior of everything. If that is true, then the warning from the Great Nothing has come for us. Our view is not the honest, average view we assumed. It is shaped by our address, and we cannot step outside the hole to check. We have been treating emptiness as the absence of a story. The opposite is turning out to be true. The empty places are screaming with information. If we can learn to listen, and listening is exactly where this gets stranger, because the void is not always silent. Sometimes, out of regions where the rules promise nothing, a signal arrives. In the year 2007, an astronomer combing through old telescope data found something that lasted less than the blink of an eye. A single, sharp spike of radio waves. Here, then gone, in a few thousandths of a second. At first it looked like noise, a glitch, but the spike had a clean shape, and it had traveled a long, long way to reach the dish. Astronomers gave this new thing a name, a fast radio burst. Then they did the math on its power, and the room went quiet. In that fraction of a second, the burst had released about as much energy as our sun pours out in an entire day. Picture every sunrise and sunset, all the heat and light the sun gives in 24 hours, crushed into a flash shorter than a camera click. Whatever made it was almost unthinkably violent, and these flashes were not rare. Once scientists knew what to look for, they started catching them across the sky, again and again. Some came from galaxies billions of light years away, so far that the light began its trip before the Earth even formed. That is the first mystery. The second is worse. Nobody knows for certain what makes them. A burst this powerful needs an engine of staggering force. The leading suspect is a type of dead star called a magnetar, a collapsed sun packed into a ball the size of a city, wrapped in the strongest magnetic field known to exist. When a magnetar twitches, it can fire off a storm of energy. That story fits some bursts well, but it does not fit all of them. The flashes come in flavors. Some appear once and never return, a single shout into the dark. Others repeat, blinking out signals over weeks and months, sometimes in patterns that almost look deliberate. Scientists are careful here. They do not call these signals aliens. The energy and timing point to natural objects, violent and strange, but natural. Still, the honest truth is that fast radio bursts remain an open mystery. We have caught thousands of them, and the full answer is still missing. For our journey, one detail matters above all. To make a burst this strong, you need a busy place. You need young, dense, dying stars. You need the crowded, fiery parts of a galaxy where stars are born and die fast. That is the rule. Big signals come from busy neighborhoods. So, when a fast radio burst arrived from a place with almost no stars at all, from the empty outskirts of a galaxy where the rules said nothing should be able to fire, astronomers had a problem. A real one. The kind that keeps you at the telescope long past midnight, asking the sky a question it has not agreed to answer. The burst was logged as a string of numbers, the way these signals always are. To keep things simple, call it the lonely burst. When astronomers traced its path backward to find the home it came from, they expected the usual story. A crowded galaxy, a busy stellar nursery, a violent place. The trail led somewhere else entirely. The lonely burst had come from the far outskirts of its galaxy, around 130,000 light-years from the bright, crowded center. To picture that, imagine a city glowing at night, full of light and motion. Now, walk past the last suburb, past the final streetlight, out into open country where the houses stop. The burst came from out there, in the dark fields where the city gives way to nothing. This was a shock. Of all the fast radio bursts ever traced, this one sat farther from the heart of its galaxy than any found before. The lead scientist on the work, a young researcher still earning her doctorate, said plainly that it was both surprising and exciting. Bursts are supposed to come from inside galaxies, often right in the star-making regions. This one came from the empty edge. So what could be making it out there, in a place where new stars do not form? That is the question that turns a fun discovery into a genuine puzzle. The usual engine, a fresh magnetar born from a recent supernova, needs young stars nearby. The outskirts have none. The stars out there, if any, are old and slow and quiet. Scientists are still circling the answer. One idea is that the burst came from an object that was flung out there long ago, a wanderer cast into the dark by some violent past. Another idea points to a strange family of old, tightly packed star clusters that can sometimes brew exotic objects. The honest status is unknown. They have the signal, they have its lonely home, the engine is still hidden. And this is the heart of our whole story, showing its face for the first time. A signal arrived from a place the rules call empty, from the kind of dark, quiet country where, by every expectation, nothing should be able to scream that loud. The universe sent a flare-up from a place that was supposed to hold no fire. Catch the pattern, because it is about to repeat in stranger and stranger ways. We keep finding strength in emptiness, voltage in the void, voices in the silence. The lonely burst was a single flash, here and gone. But not every signal from the dark is a one-time event. Some of them come back, and one of them came back from the last place in the universe a burst should ever be born. To understand why this next signal stunned everyone, you need to picture a graveyard. Out in space float tight, round balls of stars called globular clusters. Each one is a packed swarm, hundreds of thousands of suns crammed into a tidy sphere. The thing that makes them special is their age. These clusters are ancient, some of the oldest objects in the universe. The stars inside them are elderly, slow, long past their wild youth. No new stars are being born there. The nurseries closed billions of years ago. It is a retirement home for suns, quiet and dim and settled. Now remember the rule from before. A fast radio burst needs a young, violent engine, a fresh magnetar, born from a recent star death. To get one of those, you need new stars dying often, the way they do in busy galaxies. A globular cluster has none of that. It is the wrong place, the dead place, the last spot in the cosmos where you would expect a burst to fire. So when astronomers traced a repeating fast radio burst back to a globular cluster near a neighboring galaxy, the discovery did something rare in science. It made experienced researchers stop and stare. A repeating burst means the engine survived. It fired once, then waited, then fired again, blinking out energy from a swarm of old, retired stars. The signal was confirmed, tracked over time, pinned to that ancient ball of suns. The emptiness of new stars there was confirmed too. Putting those two facts together broke the simple story. How do you get a young, violent engine in a place with no young stars? Scientists came up with clever ideas to bridge the gap. Maybe two dead stars in that crowded swarm spiraled together and merged, creating something new and dangerous late in the game. In a globular cluster, the stars are packed so tightly that they bump and dance and sometimes collide, which almost never happens in open space. The crowding could be brewing rare objects long after the normal star making is over. It is a good idea. It is also still being tested. The status here sits between theory and unknown. We know where the signal lives. We are still arguing about what is making it. Step back and feel the pattern sharpening. First, a burst from the empty edge of a galaxy. Now, a burst from a graveyard of dead stars. Each time, the universe plants a roaring engine in a place built for silence. Which leads to a deeper question that has split the experts down the middle. Why do some of these signals flash once and vanish forever, while others come back again and again, like a heartbeat in the dark? The answer might mean there are two completely different kinds of monster out there, or one monster wearing two masks. Imagine you are watching for lightning in a far-off storm. Some flashes hit once and never return. Other spots flash over and over, the same patch of cloud lighting up again and again. Watching the sky, you would start to wonder, are these the same kind of lightning, or two different beasts in the same storm? That is exactly the puzzle astronomers face with fast radio bursts. They come in two clear types. The first type flashes a single time, one burst of energy, here and gone, and then silence forever. No matter how long telescopes watch that spot, it stays dark. These are the loners. The second type repeats. The same source blinks out burst after burst, sometimes spread over months, sometimes clustered into busy storms of activity. A few even seem to follow a loose rhythm, going quiet for a while, then switching back on. These are the repeaters. The split is real and confirmed. Both kinds exist, and they look different in detail. Repeaters tend to fire bursts that are a little wider in time and live in certain kinds of surroundings. Loners often look sharper. But the meaning behind the split is still open, and the experts genuinely disagree. Here is one way to read it. Maybe there are two different objects out there making bursts. One kind explodes once in a final, fatal event, a single death cry, and then it is gone. The other kind is a survivor, a battered object that keeps firing because it lives on after each blast. Here is the rival reading. Maybe there is only one kind of object, and we are seeing it from different angles, or at different ages. or in different moods. A loner might just be a repeater that we have only caught once, with the next burst still on its way, decades or centuries from now. In that case, every loner is secretly a repeater, and we simply have not waited long enough. Nobody has settled this. It is one of the live battles in the field right now. Telescopes around the world are racing to catch more bursts, to map more homes, to find the clue that tips the answer one way or the other. And while that battle plays out, the universe keeps doing what it does best. It keeps humbling us. Because for all the strange signals pouring in from billions of light years away, one of the most famous radio mysteries of recent years did not come from deep space at all. It looked exactly like a fast radio burst. It had the sharp shape, the sudden punch, the fingerprint of something far away and violent. It fooled the experts completely. And the truth, when they finally dug it out, was so close to home and so strange that it should change how you trust any signal from the sky. On a day in June of 2024, a powerful radio telescope in the Australian outback caught something sharp and bright. A quick, strong spike of radio waves, exactly the kind of fingerprint that screams fast radio burst. The team got excited. This looked like a catch from deep space, the violent flash of some distant dying object. They started to study it, the way they study every burst. Then a detail refused to fit. When a real fast radio burst crosses billions of light years of space, the long journey leaves a mark. The signal gets smeared out a little, with some frequencies arriving slightly before others, because the thin gas between galaxies drags on the wave. It is like the way a runner gets more tired the farther the race. Every true burst from far away carries this tired, smeared signature. This signal had none of it. It arrived clean and sharp, with no sign of a long trip, which meant the source was not far away at all. It was close, disturbingly close. The team took a second look at their images and found another clue. The signal had blurred in a strange way, the kind of blur you only get when something is almost right on top of you. They ran the distance. The source sat only about 2,800 miles up. That is roughly the span from New York to Los Angeles, pointed straight at the sky. This was no distant monster. This was something in our own backyard, circling the planet. After a year of digging, the team cracked it. The signal had come from a dead satellite, a forgotten relic from the Cold War era, drifting silent and useless overhead for decades. Somehow that old hunk of metal had let out a single sharp burst of radio energy, maybe a tiny spark of built-up electricity, maybe a fleck of space dust striking it at speed, a ghost twitching once in its grave. Sit with how easily it fooled everyone. The most careful astronomers on Earth, using one of the sharpest radio telescopes ever built, briefly mistook a dead satellite for a flash from the deep universe. The fingerprints matched. The trap was nearly perfect. This is why good scientists move slowly and label what they know: confirmed, possible, unknown. The universe is full of lookalikes, signals that wear the mask of something they are not, junk from human history, glitches in the gear, natural objects pretending to be exotic. That habit of doubt, of checking and rechecking before shouting an answer, is about to matter more than ever. Because the next signals on our journey do not come from satellites or from far galaxies firing once and vanishing. They come from dead stars. And these dead stars are doing something that, by the laws we trusted for 50 years, they have no right to do. They are blinking at us on a slow, steady clock from beyond a line they were never supposed to cross. To feel why the next discoveries broke the rules, you first have to meet the most reliable clock in the universe. When a giant star runs out of fuel, it dies in a massive explosion and leaves behind a tiny, crushed core. This core is a neutron star, and it is one of the most extreme things that exists. Take a ball heavier than our entire sun and squeeze it down to the size of a city only about a dozen miles wide. A single sugar cube of this stuff would weigh as much as a mountain. Some of these dead cores do something spectacular. They spin fast and they fire beams of radio waves out of their magnetic poles. As the star whirls, the beam sweeps around like the light on top of a lighthouse. Every time the beam points at Earth, our telescopes catch a pulse. Flash, flash, flash. We call these spinning beacons pulsars, and their timing is jaw-dropping. A typical pulsar can spin all the way around in a single second. Some of the fastest whip around hundreds of times every second, faster than a kitchen blender, while staying so steady that they keep better time than many clocks on Earth. That steadiness is the magic. A pulsar is a dead star that became a metronome, ticking out the seconds across the galaxy with brutal precision. But this clock has a catch, and the catch is the whole point of what comes next. A pulsar runs on its own spin. The spinning is the engine that powers the beam, and over millions of years, that spin slowly bleeds away. The star drags against its own magnetic field and gradually winds down, like a top losing its energy, turning slower and slower. As it slows, the beam weakens, and scientists worked out, long ago, that there is a limit. Spin too slowly, and the engine can no longer make radio waves at all. The lighthouse goes dark, the clock stops ticking, the dead star finally falls silent for good. This limit even has a name among astronomers. They call it the death line. Cross it, slow down past that point, and a pulsar is supposed to switch off forever. No more pulses, no more signal. Done. For 50 years, this rule held. Every spinning dead star we found obeyed it. Fast spinners blazed away. Slow ones faded toward the death line and went quiet. The pattern was clean, trusted, taught in every textbook. Then telescopes started catching pulses from objects that were spinning far too slowly to make them. Signals that, by the death line, should not be there at all. Steady, repeating, patient, coming from beyond the line where the universe promised silence, and the slowest of these blinking ghosts would turn out to be so impossible that the scientists who found it said, out loud, that it should not even exist. For half a century, the death line was a wall. On one side, dead stars that spin fast enough to blaze. On the other side, dead stars that have wound down too far and gone dark. Nothing was supposed to send pulses from the wrong side of that wall. The first crack in the wall came from a discovery that should have been quiet and turned out to be loud. Astronomers caught a signal that pulsed on a slow, steady beat. They expected the source to be a normal pulsar, one of the fast spinning beacons, so they measured how quickly it was turning. The answer made no sense. The object was spinning far too slowly to be making radio waves at all. By the death line, the rule that had held for 50 years, this thing should have been silent. A dark, dead core drifting in space. Yet there it was, firing pulses on a clock, patient and clear. This was the first of a brand new family of objects, and astronomers gave the family a careful, clunky name: long-period radio transients. Strip away the jargon, and it means a simple, shocking thing: dead stars that blink slowly, far slower than the rules allow, and keep on blinking anyway. When the first ones appeared, only a handful were known. To this day, the whole family is tiny, just about a dozen confirmed members. That rarity is part of the mystery. Are they rare because the universe makes few of them? Or rare because we never thought to look for signals this slow, and we have been walking past thousands of them in the dark? That second idea stings. Our telescopes were built to catch fast pulses, beats measured in seconds. A signal that flashes once an hour or once every few hours can slip right through our searches unnoticed. We may have been deaf to a whole population of these objects simply because we never tuned our ears to listen slow. The scientists are honest about where this stands. These objects are confirmed to exist. The signals are real, tracked, repeated. What is making them is still unknown. Something is reaching across the death line and sending out a beat that, by everything we trusted, should be impossible. The leading suspects are familiar faces in unfamiliar roles. A strange kind of dead star with a monstrous magnetic field, or a different dead star, a white dwarf, behaving in a way we have never pinned down. Or two dead stars locked in a dance, feeding off each other. The truth is still being hunted. And as the searches widened, the objects got stranger. The blinks got slower. The rules bent further. One of these signals would not just cross the death line. It would leap so far past it that the astronomers who found it reached for a phrase they almost never use about something they can clearly see in their data. They said it should not exist. Among this new family of impossible blinkers, one object stood out for a reason beyond its slow beat. It could not seem to make up its mind. Astronomers were watching a patch of sky when they caught a signal pulsing on a long, slow clock. The beat came around once every 54 minutes. For an object thought to be a spinning dead star, that is absurdly slow, far past the death line, deep in territory where the lighthouse should be dark. That alone would have made it a prize. The strangeness ran deeper. Over months of watching, the object kept changing its behavior. It had moods, 3 of them. In its first mood, it fired bright, strong pulses. Each blast lasted tens of seconds and came through clean and powerful, easy to catch. The lighthouse was blazing, then it would switch. In its second mood, the pulses dropped to a whisper, dozens of times fainter than before, short and weak. The lighthouse had dimmed almost to nothing, and in its third mood, the object simply stopped. No pulses at all, total silence. The lighthouse switched off, as if someone had cut the power. Then, later, it would wake up and start the cycle again. A normal pulsar does not do this. It picks a beat and holds it, steady as a metronome, for millions of years. This object was swinging between loud, faint, and dead silent, evolving its behavior over the months astronomers watched. Something inside it was changing, physically shifting, in a way nothing in the textbooks explained. The team did careful detective work to narrow down what it could be. They measured limits on its size and ruled out some of the simple answers. The behavior, with its sharp mood swings, reminded them most of a neutron star, one of those crushed dead cores. Yet the way it pulsed broke what we know about how neutron stars are supposed to work, especially at such a slow beat. So the verdict landed in the honest middle. The object is real and confirmed, watched and tracked through all 3 of its moods. What it actually is remains unknown. It looks like a dead star throwing pulses it should not be able to make, switching itself on and off by some hidden trigger we have not identified. Picture that, a burnt-out core of a star, supposedly past the point of making any signal at all, sitting in the dark and deciding, on its own schedule, when to shout, when to murmur, and when to go quiet. A dead thing with a will of its own. If a beat once every 54 minutes already breaks the rules, you might think it marks the far edge of strange. It does not. Another object in this family would slow the clock down so much further that 54 minutes starts to look fast. And its discoverers used the bluntest words yet. The team had been watching a faint source, hoping to learn its rhythm. The trouble was the waiting. A pulse would come, then nothing. They would keep the telescope locked on the same spot, watching, and still nothing. Minutes passed, then an hour, then more. Finally, after a long stretch of staring, the second pulse arrived. The gap between the 2 beats was 6.5 hours. Take a breath and measure that against everything you have heard so far. A fast pulsar spins around in a single second. The moody object from before took 54 minutes between blinks, and that already broke the rules. This new object took 6.5 hours to send its beat. Slower than a school day, slower than a long night of sleep. It is the slowest blinking dead star ever found, and by the laws we trusted, it is the most impossible. Remember the engine. A pulsar makes its signal from its own spin, and slowing past the death line should shut the signal off for good. This object is turning so slowly that it sits a vast distance on the wrong side of that line. The amount of power it should be able to squeeze from such a lazy spin is tiny, far too little to fire the pulses we actually see. The scientists who found it did not soften their words. according to what we know about dead stars. They said, "This object should not even exist." Those are strong words from careful people, and they said them while looking straight at the signal in their own data. The object is confirmed. The rulebook that says it cannot be there is also, as far as we knew, confirmed. Both cannot be fully right. So which is wrong? That is the thrilling part. A signal like this is a gift, because it points straight at a hole in our understanding. Either there is a new way for dead stars to make radio waves that we never imagined, some hidden engine that keeps working long past the death line, or the object is not a lone dead star at all, but something stranger, perhaps two dead stars feeding off each other in a slow, deadly partnership. The honest status, again, is unknown. We have the slowest cosmic clock in the sky, ticking once every 6.5 hours from beyond a line it should never have crossed, and we cannot yet say for sure what powers it. This is the universe handing us a riddle with the answer torn off, and every riddle like this carries the same quiet thrill. It means our map has an edge, and we have just walked past it. To find the real engine behind these impossible blinkers, scientists needed a different kind of break. They needed to catch one of these objects in the act, paired with a partner, with the smoking gun finally in view, and not long ago, they did. For a while, the slow blinkers were pure mystery. Scientists could see the signals and argue about the source, but they could not point to one and say, with confidence, here is exactly what makes it tick. The breakthrough came when a team led by a young researcher still earning his doctorate managed to pin one of these objects down across many kinds of light at once. Radio waves, visible light, ultraviolet, X-rays. By stacking all those views together, they could finally see the engine instead of guessing at it. What they found was a partnership. A pair of dead stars, locked in a tight orbit, circling each other in a deadly dance. One of the partners is a white dwarf. That is the cooling, shrunken core left behind when a star like our sun runs out of fuel and dies. It does not explode like the giants. It just collapses into a dense, glowing ember about the size of Earth, slowly fading over billions of years. The other partner is a smaller, dimmer star, close enough to be caught in the dwarf's grip. And here is the violence hiding in the dance. The dead white dwarf, with its powerful magnetic field, is pulling material off its companion, dragging it across the gap between them. As that stolen matter slams down and gets whipped around by the magnetic field, it lights up and fires off bursts of radio energy on the slow beat of their orbit. So the signal was never the spin of a single lighthouse at all. It was the rhythm of two stars circling each other, a beacon powered by theft. This mattered far beyond one object. It gave scientists their first solid proof that at least some of these impossible slow blinkers are not lone dead stars breaking the death line. They are couples. The slow beat is the orbit. The power comes from one corpse robbing another. The researchers were careful with their claim, and that care is the mark of good science. They did not announce that every slow blinker works this way. They showed that this one does, which cracks the door open and gives a clear, confirmed example to build on. Some of these signals come from white dwarf partnerships. Others might still be lone neutron stars doing something we do not understand. The family may hold more than one kind of beast. That single confirmed example is what scientists call a kind of master key, an object clear enough to help unlock the others. With it in hand, they can go back to the stranger blinkers and ask sharper questions. So the slow signals are coming into focus. Theft, orbits, dead stars draining the living. The picture is getting clearer, which means it is the perfect moment to look at how many of these hidden objects might be out there, blinking, unseen, and at the wider truth that all these discoveries have begun to whisper. We did not stop hearing these signals because the universe stopped sending them. We stopped because we forgot to listen slow, step back from the single objects and look at the whole picture, and a strange thought takes shape. Only about a dozen of these slow blinking signals have been confirmed. A dozen. In an entire galaxy of hundreds of billions of stars, we have caught barely a handful of these impossible clocks ticking in the dark. That tiny number could mean one of two very different things, and the difference matters. The first possibility is simple. Maybe these objects truly are rare. Maybe the universe only makes a few of them, through some unusual recipe, and we have found most of what exists. The second possibility is the one that keeps scientists up at night. Maybe these objects are everywhere, and we have been blind to nearly all of them. Here is why that fear is real. For decades, our telescopes and our search programs were built around speed. They hunted for pulses that flash by in seconds or fractions of a second, because that is what pulsars do. A search tuned for fast beats can completely miss a signal that only blinks once an hour or once every 6 hours. The slow pulse falls through the cracks, dismissed as noise, or never caught at all because nobody watched the same patch of sky long enough. In a real sense, we built ears for fast whispers and went deaf to slow drums. If that is true, then the dozen we have found are not the whole family. They are the few that happen to slip past our blind spots. The sky could be full of slow blinking dead stars, thousands of them, patiently sending out signals that our instruments were never set up to hear. An entire hidden population hiding in plain sight, separated from us by nothing but the speed of our own attention. Scientists are now changing how they search, deliberately watching for the slow beats, holding their gaze on patches of sky for longer, building new ways to catch a pulse that takes hours to return. Every time they widen the net, the question gets sharper. How much of the universe have we been missing simply because it moves to a slower rhythm than we expected? This is one of the quiet lessons threaded through our whole journey. Many of the strangest things in space were not hidden by distance or darkness. They were hidden by our own assumptions. We did not see them because we were sure they could not be there, so we never looked the right way. That lesson is about to get much bigger, because the next signal we visit is the most famous mystery in the history of radio astronomy. It came once, decades ago. It was so strong, so clean, so startling that the man who found it scrawled a single word beside it, and in all the years since, it has never come again. The year was 1977. A radio telescope in Ohio, nicknamed the Big Ear, was quietly scanning the sky, searching for any signal that stood out from the noise. It worked on its own, printing its readings as columns of numbers on long sheets of paper. A volunteer would check the printouts later by hand. A few days after the scan, an astronomer named Jerry Emmon sat down with the latest stack of paper and ran his eyes over the rows of figures. Most of it was the usual low hum of the cosmos. Ordinary numbers, nothing special. Then he reached a spot where the numbers jumped. For about 72 seconds, the telescope had caught a signal far louder than the background, rising up and then fading away in a smooth, clean shape. It was strong. It was narrow. It looked exactly like what scientists had imagined a deliberate broadcast from another world might look like. A sharp tone standing out from the static. Emmon was so struck that he circled the numbers in red pen and wrote a single word in the margin. Wow. That word became the name, the WOW signal, and it launched one of the longest-running mysteries in the search for life beyond Earth. For decades, people have asked the obvious, thrilling question: was it a message? The signal had several of the features you might hope for. It came in on a narrow, specific frequency, close to one that many scientists believe an alien civilization might choose. It rose and fell in just the way the telescope would record a fixed source passing through its view. But here the careful part begins, and it is the part that keeps the WOW signal honest. It happened once, only once. In all the years since, despite people pointing telescopes back at that exact patch of sky again and again, the signal has never returned. Not a whisper, not an echo, a single shout in the dark, then total silence forever. A real message, you might think, would repeat. A real beacon would call again. The endless silence afterward is the strongest argument that the WOW signal was something natural, strange, and one of a kind, rather than a hello from someone out there. So, the status of the wow signal, even now, is the most honest word in science. Unknown. Not confirmed as aliens, not explained away as a glitch, just a genuine, lingering question mark hanging over a piece of paper from 1977. For decades, it sat there, unsolved, a red circle and a one-word note. Then, recently, a team of scientists came at it from a fresh angle, and what they found did something surprising. It did not close the case, it cracked it open wider and pointed at a culprit hiding in the cold gas between the stars. For nearly 50 years, the wow signal sat unsolved, and most explanations went in circles. Maybe it was alien, maybe it was interference from Earth, some stray broadcast bouncing into the dish. Maybe it was a glitch. None of those ideas could be proven, and none could be ruled out. Recently, a team of researchers decided to attack the mystery with modern tools and a sharper map. They went back to the old data and the patch of sky it came from, and they hunted for a natural process that could fake such a strong, clean signal. What they landed on involves the cold clouds of gas that drift between the stars. Space between stars looks empty, but it is laced with thin clouds of hydrogen, the simplest and most common stuff in the universe. This hydrogen naturally gives off radio waves at one specific frequency, a kind of cosmic hum that astronomers know well. Normally that hum is faint and spread out, far too weak to look like a sharp signal, but the team proposed a trigger. Imagine a sudden, powerful burst of radiation sweeping through one of those cold hydrogen clouds, like a flashbulb going off in a dark, dusty room. For a brief moment, the cloud could light up at that hydrogen frequency, flaring far brighter than usual, then fading as the burst passed. To a telescope, that brief flare could look like a strong, narrow signal rising and falling. It could look like a wow. What could set off such a flash? Their leading idea points to a violent dead star, perhaps a magnetar, firing a sudden blast of energy, catching a nearby hydrogen cloud and making it briefly blaze. Here is the part that matters most, and the team was careful to say it out loud. Their work does not solve the mystery, it reopens it. It gives the clearest picture yet of what the wow signal might have been, and it makes the boring explanations, like simple Earth interference, far less likely. But it stops short of a final answer. The status stays at the honest edge. Possible natural cause, still not proven, still partly unknown. That honesty is worth admiring. It would be easy to grab headlines by declaring the case closed, aliens or no aliens. The scientists refused. They sharpened the map and handed the mystery forward, more focused than before, still open. And the wow signal carries a lesson that echoes through everything we have seen. A strong, clean, startling signal from the dark is not automatic proof of intelligence. The universe is a master of disguise. Dead stars, cold gas, dancing corpses, all of them can produce signals that, for a moment, look like a message meant for us. In fact, the very first time astronomers caught a steady, ticking signal from space, the most respected scientists in the field briefly wondered if they had found another civilization. The clue was so regular, so artificial looking, that they gave it a half-joking name, Little Green Men. Go back to the year 1967 to a young researcher named Jocelyn Bell, who was poring over data from a radio telescope made of wire and posts stretched across a field. She noticed something odd in the readings, a small, regular blip. It came back again and again, with a beat so precise you could set a watch by it, ticking away every few seconds like clockwork. This was a problem. In 1967, scientists knew of nothing in nature that could send out such a perfectly regular pulse. Natural objects were supposed to be messy, irregular, noisy. A signal this clean, this metronome steady, looked manufactured, made, the kind of thing a machine would produce. The possibility hung in the air, thrilling and unnerving. Had they stumbled onto a beacon from another civilization? In a moment of dark humor, the team gave the mystery signal a placeholder name, LGM-1, little green men. For a short while, the idea that this might be a message from intelligent life was on the table, taken seriously enough to whisper about. Then more of these steady tickers turned up in other parts of the sky, beating at different rhythms. It seemed unlikely that aliens would be broadcasting identical clockwork from many scattered directions at once. The truth turned out to be its own kind of wonder. Bell had discovered the very first pulsar, one of those spinning dead stars sweeping a radio beam past Earth like a lighthouse. The perfect regularity was not a machine and not a message. It was the dizzying, precise spin of a crushed dead core, turning so steadily that it mimicked something built on purpose. A natural object had perfectly imitated intelligence, and in doing so, it taught astronomers a lesson they have carried ever since. The lesson is this: nature is far more clever and far more orderly than we give it credit for. The universe is full of processes that can produce clean, regular, startling signals all on their own. A steady beat is not proof of a sender. A sharp tone is not proof of a message. Again and again, when a signal looks too perfect to be natural, the patient answer turns out to be some new and beautiful piece of physics, rather than a hello from the stars. This is exactly why scientists guard their words so carefully now. When they catch something strange, they do not leap to the most exciting conclusion. They label it confirmed, possible, or unknown, and they keep digging. The story of little green men is the reason. The first time a signal looked artificial, it was a dead star. The discipline that came from that moment has protected science from 100 false alarms since. But not every strange thing in the radio sky is a single point of light blinking on a clock. Some of them are vast. Some of them are shapes, glowing rings carved across the heavens, far larger than the galaxies they surround, with an origin that, even now, nobody can fully explain. As radio telescopes grew more powerful, they began to reveal faint shapes in the sky that older instruments had been too weak to catch. And among the strangest were enormous circles of radio light, glowing rings hanging in the dark. Astronomers gave them a plain name: odd radio circles. The word odd is doing a lot of work. These rings show up only in radio waves. Point a normal telescope at them and you see almost nothing, just empty-looking sky. Switch to radio eyes, and a vast, ghostly circle appears, a ring of glowing energy with darkness inside and out. The size is the first shock. Some of these rings are so large that an entire galaxy sits at the center of the circle like a single dot inside a giant hoop. The ring dwarfs the galaxy. If the galaxy were a coin lying on a table, the ring would be the edge of the whole table, glowing in the dark around it. So what could carve a circle that big across space? This is where the honesty kicks in, because the truth is that scientists are still working it out. Odd radio circles are a young discovery, and only a small number are known. They are confirmed to be real, mapped by more than one telescope, not a trick of the gear. What makes them is firmly in the territory of theory and unknown. One leading idea is that these rings are blast waves. Imagine an enormous explosion at the heart of a galaxy, perhaps a tremendous burst of energy from its central regions, sending a shockwave rushing outward in all directions. As that shockwave expands into space, we might be seeing it edge on as a glowing shell, a bubble of energy so large it took the blast a very long time to inflate it. The ring is the edge of the bubble, lit up in radio waves. Another idea ties them to galaxies crashing together, or to winds of charged particles streaming out of a galaxy's core and piling up at a great distance. Different teams favor different stories. No single explanation has won. What makes these rings fit our journey so well is the theme they share with everything else we have seen. They are huge structures, glowing in places where we did not expect to find anything at all, with origins that strain our understanding. A circle of light bigger than a galaxy, painted across the dark by some process we are still struggling to name. Up to now, our strange signals and shapes have lived inside galaxies, or around them, or in the empty spaces nearby. Big as the rings are, they still fit within the world of single galaxies and their neighborhoods. We are about to leave that scale behind entirely. Because the deeper our telescopes look, the further back in time they see, and out at the edge of the visible universe, in the first chapters of cosmic history, they have found things that grew too big, too fast, in an age when nothing that large should have existed yet. To look far out into space is to look back in time. The light from a distant galaxy has traveled for billions of years to reach us, so when we catch it, we are seeing that galaxy as it was long ago in the early universe. The farther we look, the younger the cosmos appears. A few years ago, humanity launched its most powerful eye yet, a giant infrared telescope built to stare deeper into that past than anything before it. Astronomers pointed it at the most distant reaches they could find, hoping to catch the very first galaxies as they switched on, just a few 100 million years after the birth of the universe. They expected to find runts, small, faint, half-formed galaxies, barely getting started, cosmic newborns. Instead, they found bodybuilders. The early galaxies coming back in the images were too bright, too big, packed with far more stars than anyone thought possible for such a young age. One scientist described the shock with a comparison that sticks. It was like visiting a far-off land and finding that many of the toddlers there weighed as much as full-grown teenagers. This was a genuine jolt, and here is why it cuts so deep. Galaxies are supposed to grow slowly, building up over billions of years. Small clumps pull together into bigger ones, which merge into bigger ones still, brick by brick, across enormous spans of time. That slow build-up is one of the foundations of how we believe the universe works. To find massive, mature-looking galaxies just a few 100 million years after the beginning is like finding a fully built skyscraper on the morning after the ground was first broken. There should not have been enough time. The bricks should still have been scattered on the ground. When these results first came in, some scientists wondered out loud whether our whole model of the universe might be broken, whether the careful theory that explains what the cosmos is made of and how it has grown since the beginning needed to be torn up and rewritten. That is a huge claim, and the field treated it with the seriousness it deserved. The galaxies themselves were confirmed, real, caught clearly in the images. The meaning was the battlefield. Did they prove our model wrong? Or was something making them look heavier than they truly were? The debate got loud. Careers and decades of established science hung on the answer. And one particular galaxy became a kind of poster child for the crisis. A single object so massive and so impossibly early that it seemed to defy everything we thought we knew about how the universe builds its giants. Among the flood of surprisingly large early galaxies, one stood out enough to become a headline of its own. It was a massive galaxy, heavier than our entire Milky Way, sitting in an age of the universe when nothing that size had any right to exist. Think about what that means. Our Milky Way is a sprawling city of hundreds of billions of stars, built up over more than 13 billion years of slow, patient growth. This early galaxy reached a comparable heft in a tiny fraction of that time, back when the universe was still young and fresh. The standard story of galaxy building goes step by step. First, invisible matter gathers into clumps. Then, gas falls into those clumps. Then stars slowly ignite, a few at a time, and the galaxy grows over ages. Each step takes time. The whole process is supposed to be gradual. This galaxy skipped to the end. It appeared massive and mature long before that slow ladder should have carried anything so high. The team that studied it called it a significant challenge to our standard model of the universe. Strong words, chosen carefully, about an object they could see plainly in their data. So the universe handed scientists a clean version of the puzzle. Here is a giant. Here is the early age when it lived. Explain how it got so big so fast, using the rules we trust. And the rules struggled. This is where the careful labeling matters again. The galaxy is confirmed. Real, measured, studied across different kinds of light. The challenge it poses to our model is also real. What it ultimately means is still being worked out. It might force a tweak to how quickly stars can form in the young universe. It might point to some deeper gap in our understanding, or it might, on closer inspection, turn out to be less impossible than it first looked, because that is exactly what started to happen as more astronomers dug into these two early giants. A few clever scientists began to suspect that the universe was playing a trick on us, that some of these galaxies were not as heavy as they seemed, that a hidden ingredient was making them shine far brighter than their true size deserved, fooling our measurements into seeing teenagers where there were only well-dressed toddlers. And the suspect they uncovered was one of the most dramatic objects in all of nature, a monster hiding at the heart of these galaxies, drinking down matter and blazing with stolen light, swelling their apparent size and shaking the whole crisis loose. The little red dots were about to change the story. As astronomers stared harder at the two early giant galaxies, they noticed that many of them shared a strange look. They were small, and they glowed with a deep red color. Scientists started calling them little red dots, a plain name for a puzzle. At first, that red glow was read as a sign of enormous mass, a galaxy crowded with countless stars. But a sharper idea began to take hold, and it pointed away from stars entirely. Lurking at the center of these dots, scientists suspected were black holes, and not quiet ones. Hungry, feeding black holes, pulling in gas at a furious rate. Here is the surprising twist about black holes. We name them for darkness because their gravity is so strong that not even light can escape once it falls in. But the area just outside a feeding black hole can be one of the brightest places in the universe. As gas spirals inward, it crowds together and rubs against itself at tremendous speed, heating up until it blazes with light, like the friction of your hands rubbing together, scaled up to a cosmic furnace. So a galaxy with a greedy black hole at its core can shine far brighter than its stars alone could ever make it. And that extra brightness is exactly the trap. When scientists measure a galaxy's mass, they often use its brightness as a guide. More light, they assume, means more stars, which means more mass. But if a hidden black hole is pumping out extra light, the galaxy looks like it holds far more stars than it truly does. We were counting the glow of the black hole and mistaking it for a crowd of suns. Take those black hole brightened galaxies out of the pile, and a load lifts. One of the lead scientists put it bluntly. The bottom line, he said, is that there is no crisis for our standard model of the universe. Once you account for the trick of the little red dots, the remaining early galaxies fit within what the model predicts after all. That is a beautiful turn, and it shows science working the way it should. A shocking result rolled in. People honestly asked whether the rules were broken. Then careful follow-up found a hidden ingredient that explained much of the mystery without tearing down the whole framework. The universe was not breaking the rules. It was wearing a clever disguise. But notice the careful word. Much of the mystery, not all of it. Some scientists still see puzzles in the early universe that the black hole explanation does not fully settle. The galaxies grew fast even after the corrections. Whether that speed bends our astrophysics or breaks something deeper is still being argued in good faith. That honest tension between a crisis averted and questions that linger is where the real frontier lives, and it leads us to the largest rule of all, the single grand assumption that holds our whole picture of the universe together. A rule that a series of impossible shapes, stretched across billions of light years, has begun to threaten. Before we reach the biggest structures in the universe, it is worth pausing on what scientists actually do when a shocking result arrives, because the story of the early galaxies is a perfect lesson in it. When those giant young galaxies first appeared, there were two ways to react. One was to shout that everything was broken, that our entire model of the universe had collapsed. The other was to ask a quieter question. Is this breaking the rules or just stretching them? There is a real difference between bending and breaking. Breaking the model would mean our deepest ideas about the universe are wrong, what it is made of, how it has grown since the beginning, the invisible matter and mysterious energy we believe fill it. Tearing those down would be one of the largest upheavals in the history of science, and it would take overwhelming evidence to justify. Bending the model is gentler. It means the big framework still stands, but some smaller piece needs adjusting. Maybe stars formed faster in the early universe than we assumed. Maybe black holes lit up sooner than expected. The foundation holds. We just learned a new detail about how things played out on top of it. So far, the early galaxy crisis looks more like a bend than a break. The hidden black holes of the little red dots eased most of the strain. The standard model took a hit, wobbled, and stayed standing. As one scientist wisely noted, when a theory has survived the test of time for so long, you need overwhelming proof before you throw it out. That caution is not stubbornness. It is wisdom earned through a century of false alarms, of signals that looked like aliens and turned out to be dead stars, of galaxies that looked impossible and turned out to be wearing makeup. The universe loves to startle us, and then, on closer inspection, to reveal a subtler truth. Hold that lesson tight, because we are about to test it against the hardest cases yet. Everything so far has lived at the scale of stars and single galaxies, or the young universe seen as a whole. Strange signals, impossible blinkers, galaxies that grew too fast. Each one challenged a rule, and most of them ended up bending it rather than breaking it. Now we go bigger than galaxies, bigger than clusters of galaxies. We go to structures so vast that they stretch across a meaningful slice of the entire visible universe. Shapes made of thousands of galaxies strung together into rings and arcs. These giants test the single most important assumption in all of cosmology, the bedrock idea that lets us trust everything else. And unlike the early galaxies, the strain they put on the rules has not yet been explained away. They may be the closest thing yet to a crack in the foundation. To understand why, you first need to meet the rule they threaten. There is one assumption holding up nearly everything we believe about the universe. It is so basic that it sounds almost too simple to matter. Scientists call it the cosmological principle. Here is what it says. On a large enough scale, the universe looks the same everywhere, and it looks the same in every direction. No special places, no special directions. Zoom out far enough, and every giant chunk of space should look pretty much like every other. Picture a vast ocean seen from high above. Up close, the surface is all detail, waves and foam and ripples. But pull back far enough, and the whole ocean smooths into a flat, even blue, the same in every direction you turn. The cosmological principle says the universe is like that, lumpy and detailed up close, but smooth and even when you stand back. This rule is the foundation under the whole building. It is the reason we trust our measurements at all. Remember the warning from the voids, the fear that our address might be lying to us. The cosmological principle is the promise that says it is not, that our patch of space is a fair sample of the whole, so what we measure here can be trusted to describe everywhere. If the principle holds, science can stand on solid ground. We can take what we see in our corner and apply it to the entire cosmos with confidence. Almost every map, every model, every grand claim about the universe leans on this single idea. So the principle comes with a hard prediction, a line in the sand. There should be a limit to how big any single structure in the universe can be. Galaxies can gather into clusters. Clusters can string into threads and walls. But past a certain enormous size, the lumpiness has to smooth out. Nothing should be able to grow bigger than that limit, because beyond it, the universe is supposed to be even and featureless. The smoothness has to win. Scientists have even worked out roughly where that ceiling sits. There is a size, vast almost beyond imagining, above which no single structure should exist. Cross that line, and you are no longer looking at a lump in a smooth universe. You are looking at something that should not be possible if the principle is true. For a long time, the largest things we found stayed under the ceiling, more or less. The principle held. The foundation felt secure. Then, a graduate student, doing patient work with maps of distant galaxies, noticed something stretching across the sky. A shape. A curve made of galaxy clusters, far too long to be a coincidence. When she measured it end to end, the number she got blew straight past the ceiling, and it was only the first of the giants she would find. The student's name is Alexia Lopez, and she was working her way through a vast map of the distant universe, studying the light of faraway galaxies, when a pattern caught her eye. Spread across a huge stretch of sky was a curve, an arc made of galaxy clusters and the gas around them, all lined up at the same enormous distance from Earth, all sending their light from a time when the universe was about half its current age. The galaxies traced a gentle bend, like a smile carved across the heavens. She had to be careful. The human eye is a pattern-finding machine, and it loves to see shapes where there are none. Stare at clouds long enough and you find faces. Lopez knew this danger well, so she ran the numbers. She used statistical tests to ask a cold question. Could this arc be a random accident? A trick of scattered galaxies that just happened to line up? The tests said no. The arc was unlikely to be a coincidence. It looked like a real structure, thousands of galaxies bound into a single curving shape. Then she measured its length, and the size was staggering. The giant arc, as it came to be called, stretches across roughly 3 billion light-years. 3 billion. That is a meaningful slice of the entire visible universe. A single object so long that light itself would need billions of years to travel from one end to the other. Now bring back the ceiling. The cosmological principle says no structure should grow past a certain limit, and that limit, while vast, is a good deal smaller than the giant arc. The arc does not nudge against the line. It towers over it, several times larger than the size where the universe is supposed to smooth out. By the rule that holds up modern cosmology, this thing should not exist. That is the collision at the heart of the discovery. On one side, the giant arc, mapped and tested, and standing in the data. On the other side, the cosmological principle, the trusted foundation under all our cosmic confidence. They cannot both be completely right. Either the arc is somehow a fluke our tests failed to catch, or our most basic rule about the universe has a problem. Scientists, being careful, did not rush to crown a winner. The arc is intriguing, even unsettling, and the debate over what it means is still wide open. Some researchers accept it as a real challenge to the principle. Others suspect our eyes and our methods are still fooling us, finding a shape in the scatter. The honest label is contested, a real measurement, a fiercely argued meaning. You might hope this was a one-off, a single strange giant that could be brushed aside as a rare accident. The universe did not grant that mercy, because the same student, looking in the same region of the sky, soon found a second monster sitting right beside the first. And two impossible giants, side by side, are much harder to explain away than one. Not long after the giant arc, Alexia Lopez was studying the same patch of the distant sky when another shape emerged from the data. This one was not a curve, it was a closed loop, a ring, made of galaxies and galaxy clusters strung together. This enormous circle hung in space, facing almost straight toward Earth, like a vast, cosmic eye looking back at us. She tested it the same careful way she had tested the arc, running the statistics to rule out a lucky accident. Again, the tests said the shape was unlikely to be random. The ring looked real. Its size matched its strangeness. The big ring measures more than 1 billion light-years across. Trace the full circle, all the way around, and the loop runs about 4 billion light-years in circumference. It sits at a tremendous distance from us, around 9 billion light-years away, so its light set out when the universe was young and the sun did not yet exist. And here is the detail that makes scientists uneasy in the best way. The big ring sits in the same region of the sky as the giant arc, at nearly the same distance, in the same slice of cosmic time. The two giants are neighbors, cosmic next-door neighbors, separated by only a small gap in the sky. Think about how strange that is. The cosmological principle says huge structures should be vanishingly rare, so rare that we might expect to find only one truly enormous structure in the entire observable universe, if any. Yet here are two of them, both larger than the ceiling allows, sitting right next to each other in the same neighborhood. Finding one impossible giant could be shrugged off as a freak event. Finding two, side by side, is far harder to dismiss. It starts to look less like a coincidence and more like a pattern, a hint that something about this region, or about the rules themselves, is not what we assumed. The scientist who found them said it plainly. Neither of these ultra-large structures is easy to explain in our current understanding of the universe. Their sizes, their shapes, and their closeness must be telling us something important. The trouble is that nobody is sure what. The status of both giants stays in honest, open territory. They are measured, they are tested, they are argued over, they are not yet confirmed beyond all doubt, and they are not yet explained away. They sit on the live frontier, where the foundation of cosmology meets shapes it cannot easily account for. So we are left with a sharp, thrilling problem. We have two structures that, by the rules, should not be there, which raises the obvious question. Just how far past the limit do these giants reach? And what could possibly be powerful enough to carve shapes so vast across the early universe, if our trusted rule cannot? The answers run from the cautious to the wild, and they pull us toward the strangest edges of physics. To feel the full weight of these giant structures, you have to put their size right next to the ceiling they are supposed to obey. Scientists have calculated the rough upper limit for any structure in the universe. Above that size, the cosmological principle says, the lumpiness has to smooth out and nothing larger should exist. That limit is already vast, well over 1 billion light-years. Now lay the giants against it. The Big Ring's circumference runs to about 4 billion light-years. The giant arc stretches around 3 billion light-years, end to end. Both of them sail clean past the ceiling. The arc is several times longer than the size where the universe is supposed to go smooth. These are not structures that barely nudge over the line. They tower above it. If the cosmological principle is correct, the universe should not be able to assemble anything this large anywhere, let alone two such things side by side. So scientists are left with a small set of uncomfortable choices, and each one is interesting. The first choice is that the structures are not truly real in the way they appear. Perhaps our pattern-finding eyes and our methods are still tricking us, stitching scattered galaxies into shapes that do not really hold together as single objects. Some researchers lean this way, and their doubt is healthy. It keeps the field from leaping to wild conclusions. The second choice is that the structures are real, and our most basic rule needs rethinking. Maybe the universe is not as smooth and even on the largest scales as we assumed. Maybe there are special regions, special patterns, that the cosmological principle does not capture. That would be a deep and serious shift, the kind that takes years and mountains of evidence to accept. The third choice is the most exciting. Maybe the structures are real, the principle mostly holds, and these giants were carved by some force from the early universe that we have only begun to understand. Some process powerful enough to draw shapes billions of light-years wide across the young cosmos, leaving rings and arcs as its fingerprints. That third path is where physics gets strange and beautiful, because to explain shapes this enormous, some scientists have reached for one of the wildest ideas in all of cosmology: threads in the fabric of space itself, born in the first instance after the beginning, thinner than the smallest particle yet stretching across the universe. If they exist, they could change everything, and the case for them, strange as it sounds, is built on serious physics. Before we chase the wildest explanation, honesty demands that we sit with the doubters, because their argument is strong and it keeps the whole field grounded. Here is the worry. The human brain is built to find patterns. It is one of our greatest gifts and one of our deepest traps. We see faces in the moon, animals in the clouds, shapes in the static. Our ancestors who spotted the tiger hiding in the grass survived, so evolution wired us to find form everywhere, even where there is none. Now point that pattern-hungry brain at a map of millions of scattered galaxies. With so many dots spread across the sky, some of them will, by pure chance, line up into curves and loops and arcs. Not because they are bound together, just because randomness, given enough points, always coughs up shapes that look meaningful. So when someone announces a giant ring or a giant arc, careful scientists ask the hard question: is this a real structure, with the galaxies truly connected across space? Or is it a mirage, a chance alignment that our eager eyes have promoted into an object? This doubt is not an attack, it is the immune system of science. The researchers who found the giants ran statistical tests precisely to answer it, and those tests suggested the shapes were unlikely to be random. But statistics on the larger scales are slippery. Critics argue that the tests can be fooled, that the way we search for structures can accidentally create them, finding what we set out to find. Many cosmologists remain unconvinced that these giants break the cosmological principle. They point out that a few large structures, on their own, might not be enough to topple a rule supported by so much other evidence. They would rather adjust their idea of what counts as a fair sample than tear down the foundation over a handful of contested shapes. So the field sits split. On one side, those who see the giant arcs and rings as genuine cracks in our model, signals that the universe is stranger than our rule allows. On the other, those who suspect we are seeing tigers in the grass, shapes our minds built from random scatter. The honest status is unresolved. A real debate, fought with real data, still open. That tension is exactly what a healthy frontier looks like. Not a settled answer, but a live argument between careful people who all want the truth and disagree about what the evidence shows. And yet, suppose the giants are real. Suppose those rings and arcs truly are bound structures too large for our rules. Then we need a force that could have drawn them, something that reached across the young universe and sculpted matter into shapes billions of light years wide. For that, a handful of physicists have revived an idea so strange it sounds invented. Cracks in space itself, left over from the birth of everything, thinner than a proton and longer than galaxies. They are called cosmic strings, and they might be real. To picture a cosmic string, start with something familiar: a lake freezing on a cold night. As the water turns to ice, it does not freeze perfectly smoothly. Cracks and flaws form, lines of stress frozen into the sheet where different patches of ice met and could not quite line up. Some physicists believe the early universe did something similar. In the first, unimaginably tiny fraction of a second after the beginning, as the cosmos cooled at a staggering rate, the fabric of space itself may have frozen with flaws. Long, thin lines of trapped energy, left over from that violent birth, threaded through the young universe, like cracks in cooling ice. These hypothetical flaws are called cosmic strings, and their properties are almost impossible to believe. A cosmic string would be unthinkably thin, far narrower than a single proton, one of the tiny particles inside an atom, thinner than the smallest piece of matter you have ever heard named. And yet a single string could stretch for billions of light years, reaching clear across a huge swath of the universe. Imagine a thread finer than anything that exists, longer than anything that exists, humming with the energy of creation. Despite being so thin, a cosmic string would carry enormous mass packed along its length, and mass means gravity. As such a string moved through the early universe, its gravity could tug on the matter around it, herding gas and the seeds of galaxies, nudging them into line. Over cosmic time, that gentle herding might pull galaxies into vast patterns, into arcs, into rings, into the very shapes that should not exist. That is why a few scientists have pointed to cosmic strings as a possible explanation for the giant arc and the big ring. If a string carved through that region long ago, it could have sculpted matter into the giant curves we now struggle to explain, leaving its fingerprint written across billions of light years. Now, for the crucial honesty. Cosmic strings have never been found. They are pure theory. a serious and respected idea in physics, but unconfirmed, sitting firmly in the realm of the unknown. No telescope has ever caught one. They might fill the universe, unseen. They might not exist at all. So the explanation comes wrapped in a question mark, and that is exactly right. We have impossible shapes that may or may not be real, possibly carved by invisible threads that may or may not exist. Mystery layered on mystery, each one honest about how little we truly know. We have come a long way, from a single empty void to giant rings and the cracks of creation. But there is one more place to visit, and in some ways, it is the strangest of all, a cold spot in the oldest light in existence, the faint afterglow of the universe's birth, a patch that should be smooth but is not, and the wildest idea about what made it reaches beyond our universe entirely. Everywhere you look in the sky, in every direction, there is a faint glow left over from the birth of the universe. It is the oldest light there is, released when the cosmos was very young, and it has been traveling toward us ever since. Astronomers call it the afterglow of creation. It fills all of space, a gentle hum of ancient light. This afterglow is almost perfectly even, the same faint warmth in every direction, exactly as the cosmological principle promises. When scientists mapped it across the whole sky, they found it smooth to an astonishing degree, with only the tiniest ripples of slightly warmer and slightly cooler patches. Then they found a spot that was too cold. In one region of the sky sits a patch of the afterglow that is noticeably cooler than it should be. A cold spot, larger and deeper than the gentle ripples around it. It stood out enough that scientists have puzzled over it for years, asking what could chill a piece of the oldest light in the universe. One leading explanation ties it back to where our journey began: voids. Remember how the light from creation has to cross the entire universe to reach us, passing through everything in its path. If that ancient light traveled through an enormous void, a vast region emptier than anything around it, the journey could drain a little energy from the light, leaving it slightly colder when it finally arrives. The cold spot in this story would be the shadow of a supervoid, a hole in space so large that it left its mark on the afterglow of creation itself. There is real evidence pointing toward a large, underdense region in that direction, which fits the idea well, so the supervoid explanation sits in respectable territory, supported but not fully settled, a strong possibility, still being checked. That alone is a wonderful thought, the biggest emptiness leaving a fingerprint on the oldest light, the void and the afterglow, connected across the whole history of the universe. But the cold spot has also attracted an idea so wild that most scientists keep it at arm's length, mentioning it carefully with heavy warnings. An idea that the cold spot is not the shadow of a void at all, but something far stranger, a bruise, a mark left on our universe by a collision with another one. It lives at the far edge of speculation, unproven and unlikely, and yet it is exactly the kind of question these mysteries push us toward, when the ordinary explanations strain and the mind reaches for something more. The idea is so strange that it needs a clear warning before we even describe it. What follows lies at the wild, unproven edge of physics. Most scientists treat it with deep caution. It is speculation, flagged as speculation, offered as a thought rather than a finding. Hold it lightly. With that said, here is the idea. Some physicists explore the possibility that our universe is not the only one. In certain theories, our cosmos is one bubble among many, floating in a far larger space, with other universes bubbling alongside it. We cannot see them. We cannot reach them. They would exist completely beyond our view, separate realities running their own rules. Now imagine, long ago, in the chaos near the birth of everything, two of those bubbles drifting close and touching. A collision between our universe and another, brushing against each other for an instant in the deep past. A few researchers have wondered whether such a collision might leave a mark, a bruise, pressed into the fabric of our universe at the point of contact that could still be faintly visible today in the oldest light. And they have asked, quietly and carefully, whether the cold spot could be that bruise, a scar from the moment our universe bumped into another one. Sit with how staggering that would be, even as a remote possibility. It would mean the cold patch in the sky is a window, not into our own past, but into the existence of entire other universes beyond our own. Proof that we are one bubble among countless others, marked forever by a touch from outside everything we can see. Now the honesty, which matters more here than anywhere. This idea is not confirmed. It is not even close to confirmed. It sits at the far fringe of serious physics, an interesting thing some scientists are willing to explore, while most regard the simpler explanations as far more likely. The supervoid story is the calmer, better supported answer. The collision idea is the wild card, fun to consider, light on proof. But notice why the idea exists at all. It exists because the cold spot is a genuine puzzle, a feature in the afterglow that our simplest expectations did not predict. When the universe shows us something it should not, our minds stretch toward bigger and bigger explanations, all the way out to other worlds. That stretching is not foolishness. It is the same restless curiosity that has driven every discovery on this entire journey. And that brings us, at last, to the thread that has run through everything, through the empty void and the lonely galaxies, through the impossible blinking stars and the signals from nowhere, through the giant rings and the cold spot in the oldest light. Every one of these mysteries shares a single, quiet message about us, and about how much of the universe we still have left to understand. It is the most important idea of all, and it changes how you should feel the next time someone tells you that something is impossible. Look back at the whole journey, and a pattern rises up, clearer than any single mystery. We began with a hole in the universe, so empty that astronomers thought their machines were broken. We met galaxies so lonely that a civilization living among them might believe it was utterly alone. We found that we, too, live inside an emptier patch of space that may be quietly skewing our view of everything. We chased signals from places where the rules promised silence, bursts from the empty edges of galaxies and from graveyards of dead stars. Dead stars blinking far past the line where they should have gone dark, one of them so slow and so impossible that its discoverers said plainly it should not exist. We watched a humble dead satellite fool the sharpest minds on Earth and learned why scientists guard their words with such care. We saw galaxies that grew too big too fast and watched a crisis bend rather than break as a hidden trick of black holes came to light. We stood before structures billions of light years wide, rings and arcs that tower over the limit our deepest rule allows. And we ended at a cold spot in the oldest light, shadowed perhaps by a supervoid, or, in the wildest dream, bruised by another universe entirely. Every one of these began the same way. Something appeared where nothing should have been, a signal, a shape, a giant, an emptiness. Each one seemed to break a rule we trusted. And here is the thread that ties them together. Almost every time the universe showed us something impossible, the impossibility was not in the cosmos, it was in our map. The voids were screaming with information we had dismissed as empty. The slow signals were everywhere, missed only because we listened for fast ones. The giant galaxies wore a disguise. Again and again, the word impossible turned out to mean something humbler and more thrilling. We have reached the edge of what we know. That is what a strange signal really is. It is the universe pointing at a gap in our understanding and inviting us to fill it. Every mystery on this journey is a door, and behind each door is a piece of reality we have not yet learned to see. For you, watching this, that is the part worth carrying. The universe is not finished surprising us. The textbooks are not the final word. Out there, right now, are signals arriving from places our rules call empty, shapes too large to allow, objects that should not exist. And somewhere, a curious person, staring at a screen full of data, is about to circle something strange and write a single word in the margin. The map of everything has an edge, and the edge is moving. Every impossible thing we have ever found turned out to be a new room in a house far larger than we imagined. The next signal could open a room no one has ever entered. So the next time you hear that something cannot exist, remember the void, the blinking dead star, the ring too big for the sky. Then look up and wonder what we have not yet learned to hear.